July 1st, 2025. Rio Hurtado, Chile. Just before dawn, a survey telescope built to catch asteroids on a collision course with Earth flags something else entirely, a point of light moving far too fast to belong to our solar system. Astronomers confirm it within days. Only the third interstellar object ever detected, after one in 2017 and one in 2019. Its orbit is the most extreme of the three, tilted almost sideways, moving in the opposite direction of everything else in the solar system. In the first days after discovery, early brightness estimates suggested it might be up to 20 kilometers wide, the largest interstellar object ever seen. Weeks later, once the Hubble Space Telescope resolved it directly, that number collapsed to somewhere under 6 kilometers. A Harvard astrophysicist takes one look at the numbers and says, in public, that it might not be a comet at all. It might be a probe. 4 months later, NASA holds a press conference to answer him directly. This object is a comet, says NASA Associate Administrator Amit Kshatriya. It looks and behaves like a comet, and all evidence points towards it being a comet. That argument, one scientist convinced we might not be alone, an entire agency convinced we are, is not new. It is 75 years old, and it started almost by accident at a lunch table. You're watching Mindwired. This is the real story of the Fermi Paradox, the offhand question that became a 75-year argument, the real scientists who tried to answer it, and the two live, unresolved cases, one from 2025, one still running in 2026, that show exactly how close and how far we actually are. Chapter 1. The lunch nobody wrote down. Summer 1950. Los Alamos, New Mexico. At a lunch table inside Fuller Lodge, physicist Enrico Fermi sits down with three colleagues, Emil Konopinski, Edward Teller, and Herbert York. On the walk over, the four men had been talking about a New Yorker cartoon published a few months earlier. A flying saucer and little green men carrying off the neighborhood's trash cans, poking fun at a real, minor 1950 news story about missing garbage cans in New York City. Then, with no warning, Fermi asked a question that had nothing to do with anything they'd been discussing. Konopinski remembered it as, "But where is everybody?" Teller remembered the same four words. York remembered it slightly differently. "Don't you ever wonder where everybody is?" Everyone at the table understood immediately. He meant extraterrestrials. Fermi followed up with his own back-of-the-envelope math, the odds of other Earth-like planets, the odds of life, the odds of intelligence, and concluded that, statistically, we should have been visited long ago, and many times over. Here's the honest part almost nobody mentions. The three men who were actually there never agreed on when it happened. York said 1951. Teller, separately, said probably before 1950. A Los Alamos historian spent decades trying to pin the date down and settled on 1950, based on how fresh a cartoon still felt in one man's memory 34 years later. Fuller Lodge is still standing today in downtown Los Alamos. The actual room where this happened is a museum you can walk into. Chapter 2. The name took 27 years to attach. Fermi never published his question. He never gave it a name. The idea just sat there, unrecorded, until a young astronomer named Carl Sagan mentioned it in a footnote 13 years later. In 1975, astronomer Michael Hart published the first rigorous version of the argument in a British astronomy journal. His paper never once mentions Fermi's name. It never uses the word paradox. Hart's argument didn't stop in 1975. In 1980, physicist Frank Tipler extended it into what's now called the Hart-Tipler conjecture, an even harder-line version of the same case. That same year as Hart's paper, engineer David Viewing published a separate paper that finally called it a paradox and credited Fermi by name for asking the original question. The exact phrase Fermi's paradox didn't appear in print until 1977, coined by physicist David Stevenson, who later admitted he only put quotation marks around it as, in his words, an apology for using a short, convenient label for a much messier argument. The man everyone credits never wrote the paradox down. Three other men, spread across 2 years, built the argument and gave it his name, without him. Chapter 3. The same argument got a formula 11 years later. A year before that, Frank Drake had already run the very first real search for alien radio signals, Project Ozma, pointed at two nearby stars, spring of 1960. It found nothing, but it proved the search itself was possible. November 1st, 1961, Green Bank, West Virginia. Drake gathers 10 scientists for a meeting that would define how the search for alien life gets talked about to this day. On the first morning, Drake writes 7 variables on a chalkboard: the rate stars form, the fraction with planets, the fraction that could support life, and so on, multiplied together into a single number. It becomes known as the Drake equation. One variable in that equation is called L, how long a civilization survives before it goes silent. Drake built it that way on purpose. It was 1961. The Berlin Wall had gone up 2 months earlier. Every scientist at that table was living through the real possibility of nuclear war. A radio astronomer named Sebastian von Hoener had already put a number on that fear. 60%, he estimated, was the chance any civilization wipes itself out with nuclear war once it reaches that stage. Soviet astronomer Iosif Shklovsky later grew so convinced of it that he renounced the search for alien signals entirely. In 1966, Shklovsky and Carl Sagan co-wrote an entire book built around that same uncertain lifespan. Sagan brought the same warning to a mass television audience in 1980 on Cosmos. Chapter 4. We finally have real numbers to plug into that formula. For years, the working number was tiny. Of NASA's Kepler telescope's first 1,000 confirmed planets, only about a dozen were even close to Earth's size and sitting in the right zone. For the first 4 decades after that chalkboard, nobody could fill in Drake's equation with anything but guesses. There were 0 confirmed planets outside our solar system. Then, in 1995, that changed. 30 years later, NASA has confirmed more than 6,000 exoplanets, with billions more believed to exist across the galaxy. Narrow that down to planets actually sitting in the habitable zone, rocky, roughly Earth-sized, the right distance from their star, and a 2026 catalogue from Cornell's Carl Sagan Institute finds exactly 45 real candidates. Even that number is a moving target. Depending on the study, the fraction of Sun-like stars with a truly Earth-like planet ranges anywhere from 1% to as high as 40%. We've never actually finished counting. We've extrapolated. NASA's newer TESS telescope isn't overturning that picture. It's sharpening it, tightening the uncertainty around numbers Kepler could only estimate. This is a number actively being worked on right now, not one anybody's finished with. Chapter 5. Is the worst part behind us or still ahead? In 1996, an economist, not an astronomer, named Robin Hanson wrote an essay that reframed the entire question. He called it The Great Filter. Somewhere on the path from dead matter to a galaxy-spanning civilization, at least one step is so improbable that almost nothing ever makes it through. His own words, "The easier it was for life to evolve to our stage, the bleaker our future chances probably are. If most of the filter is already behind us, our future is wide open. If it's still ahead, something is coming that we haven't survived yet, in any case we know of." Philosopher Nick Bostrom, then at Oxford's Future of Humanity Institute, took the ahead of us version seriously enough to publish a 2008 essay literally titled "Why I Hope the Search for Extraterrestrial Life Finds Nothing." Among his candidates for a filter still ahead of humanity, superintelligent artificial intelligence with destructive goals. Not every scientist agrees a filter is even needed. In 2018, 3 Oxford researchers argued the paradox might simply dissolve once you model real statistical uncertainty into Drake's equation, raising the odds that we are simply, quietly, alone in this galaxy to as high as 99.6%. Toby Ord, also of Oxford, later estimated our own generation faces roughly a 1 in 6 chance of civilization-ending catastrophe this century, nuclear war, engineered pandemics, and unaligned artificial intelligence among the largest contributors. If a filter really is ahead of every civilization, we may be standing inside it right now. Chapter 6. Maybe the rare part isn't life, it's us. Ward and Brownlee's collaborators went even further, proposing a galactic habitable zone, The idea that only certain regions of the Milky Way, at the right distance from the crowded, radiation-heavy galactic center, can support complex life at all. One of that paper's own co-authors later became linked to intelligent design advocacy in a separate, far more controversial book, a reminder to judge each paper on its own record, not by association. In the year 2000, geologist Peter Ward and astronomer Donald Brownlee proposed a different answer entirely. Simple microbial life, they argued, might be everywhere. Complex life, anything bigger than a microbe, might be almost impossibly rare. Their case rests on a list of coincidences. A moon just large enough to stabilize our planet's tilt, plate tectonics that recycle carbon and keep the climate survivable for billions of years, a magnetic field shielding the atmosphere from the sun's radiation. They also argued Jupiter acts as a gravitational shield, sweeping up comets before they reach us. A later three-part study directly challenged that claim. Finding a Jupiter-sized planet doesn't clearly reduce the danger at all. For some kinds of impacts, it can even make things worse. Other scientists pushed back hard on the whole idea. One reviewer called it restrictive and unimaginative, a kind of circular reasoning that just describes the one planet we happen to live on and calls it a rule. Chapter 7. The theory that says silence might be the only rational choice. In 2008, Chinese novelist Liu Cixin, not a scientist, a novelist, published a science fiction idea that would eventually leak into real scientific debate. He called it the Dark Forest. Every civilization is a silent, armed hunter, unable to ever verify another civilization's intentions. So the only rational move is total silence, and the only rational response to being noticed is to strike first. The idea itself is older than the novel. Astronomer David Brin raised a nearly identical deadly probes concern back in 1983. And it's the exact logic Avi Loeb reached for in 2025 when he floated the possibility that the object from our cold open could be reconnaissance, not just rock and ice. But even Loeb doesn't claim certainty. In his own words, this object is most likely a comet of natural origin. He rates his own alien technology hypothesis a 4 out of 10 on a scale he invented himself. Penn State astronomer Jason Wright, who runs his own search for alien technology for a living, published a point-by-point rebuttal of every claimed anomaly. 2 separate radio observatories listened to the object during its closest approach. Neither one heard anything. A gentler version of the same silence idea came decades earlier. In 1973, Harvard radio astronomer John Ball proposed the zoo hypothesis. Maybe advanced civilizations already know we're here and are simply choosing not to interfere, the way a visitor at a nature reserve watches without stepping inside the fence. It's a real, citable, seriously discussed idea. It's also, by its own logic, impossible to disprove. Any silence at all is consistent with a civilization that's simply choosing to watch quietly. Physicist Stephen Hawking made a similar argument in a very different context back in 2010, warning that broadcasting our location to the universe could be like Native Americans first encountering Columbus. He never used the phrase dark forest. The novel that coined it wouldn't be translated into English for another 5 years. That same caution shows up in a real, non-fictional policy fight. In the 2010s, several senior scientists linked to the search for alien signals resigned from committees to protest loosened rules on deliberately transmitting messages toward other stars, arguing that broadcasting our location without asking the rest of the planet first is a risk no single group has the right to take. Chapter 8. The signal that almost was. 124 light-years away, there's a planet called K218b, bigger than Earth, smaller than Neptune, sitting in its star's habitable zone. For 3 straight years, it has been at the center of the closest real scientific fight over whether we've actually detected life anywhere else. September 2023. Cambridge astronomer Niku Madhusudan's team uses the James Webb Space Telescope and detects methane and carbon dioxide in its atmosphere, plus a faint, tentative hint of something else, dimethyl sulfide, a gas that, on Earth, is produced almost exclusively by marine microbes. April 2025. The same team publishes a new observation with a different instrument, reporting the signal again, this time at roughly 3 sigma confidence. Cambridge's own press release calls it the strongest hints yet of biological activity outside the solar system. Madhusudan himself was careful. "It's important that we're deeply skeptical of our own results," he said, "because it's only by testing and testing again that we will be able to reach the point where we're confident in them." 3 sigma sounds impressive. A real discovery claim in physics needs 5. Within weeks, NASA scientist Renyu Hu reanalyzed the same data with additional observations. He confirmed the methane and carbon dioxide again, but found the dimethyl sulfide signal only marginal and identified ordinary, non-biological chemistry that could produce the same gas without any life at all. 2 more independent teams ran the exact same raw data through their own statistical models. One found the signal supported in just 12.5% of their tests and traced most of it to unresolved instrument noise, not chemistry. Their conclusion, in their own words, there is, as yet, no statistically significant evidence for biosignatures. By March 2026, the newest paper on K218b doesn't even try to settle the biosignature question anymore. It argues the more basic physics of the planet, what its interior is even made of, has to be nailed down first before anyone can evaluate a claim like this at all. So here is where it actually stands, right now. A real signal, detected twice by the same team, using real telescope data that has so far failed to survive 3 independent attempts to reproduce it. Not disproven. Not confirmed. Genuinely, actively, still open. Chapter 9. Back to the object that started this video. The interstellar object from our cold open passed its closest point to the Sun at the end of October 2025, and it has been fading ever since. By December, it required a serious telescope just to see it all. It will never come back. It is now heading out of our solar system for good, on a path that will not bring it near the inner planets again for thousands of years. But the story isn't closed. New peer-reviewed papers on this object kept publishing well into 2026, a methane detection in June, and a study months earlier, in May, of unusually heavy water that the researchers themselves say points to the object forming around a much older, colder star than our own Sun. And Avi Loeb is still posting. His tally of anomalies kept growing well into 2026. Jason Wright's rebuttals kept coming right back. As of this video, that argument has no scheduled end date. Astronomer Nathalie Cabral, who leads the search for life at the Carl Sagan Center, put the bigger shift in perspective. Planets became the rule, not the exception. Every year, the old excuse that maybe habitable planets are just rare gets a little harder to use. Here's what actually stays with me. 2 real, live cases, 1 object, 1 planet, got about as close as anyone alive has ever gotten to answering this question. And both of them, honestly, ended in the exact same place. Not yes, not no. Still open. That's not a failure. 75 years ago, this entire argument existed because one physicist asked a question at lunch that nobody could even begin to test. Today, we have real telescopes pointed at real atmospheres, 124 light years away, arguing over real data. We haven't answered Fermi's question. We've finally earned the right to actually ask it properly. Fermi never got his answer. Neither have we. But for the first time since that lunch table in 1950, we're close enough to be genuinely, uncomfortably unsure. And that unsureness is the most honest place this question has ever been. If 2 live cases like this got under your skin, wait until you see the message we already sent out into the dark, on purpose, in 1977, and what would actually happen if anyone ever found it. That full story is live on this channel right now. Subscribe to Mindwired. If any of this messed with your head a little, well, that's exactly the point. And it only happens because people like you keep showing up. And
hit subscribe right now for it. It costs you nothing, and it's the entire reason Mindwired keeps making videos like this. Subscribe.